So good evening and good afternoon, all learners, and thank you everybody for registering to the Parallel Computer Architecture course. And I'm very happy that you have, I would say, taken the challenge to do this course, because after doing a basic computer organization course and an advanced architecture course, one feels that yes, we know a lot of our computer architecture and there is no more need to learn anything further. But it is good on your part to have registered for this course, because it covers most of the fundamentals of parallel architecture. And as we move on from here in the new generation, we are going to see a lot of use of these parallel concepts because of the boom of ML and AI coming in. So a lot of parallel processing needs to be done, and having understanding of the basics is very good to know. Okay, so thank you, and we are presently attending the first live session of this course of the year 2025. I had only a few questions posted by some of the learners. The first question actually deals with DeepSeek as an LLM model, and the student was curious as to how have they managed to reduce the number of GPUs and what is its impact. But I would kind of disappoint the student, because I have no understanding of the model as such and how have they reduced the GPU usage. Maybe we can take these discussions offline and not in a live session. So if you are still interested, if the questions are related to the topic but not directly into the content of the subject, then you can contact us offline or paste questions in the mailing list. Okay, so thank you for your query, but I cannot take that right now. There was another question which was asking for some iPhone security query. So I'm again sorry, I cannot take that question. If you have any doubts for those who are attending, you can type your questions in the chat box and we'll be happy to answer them. Okay, so there was another question from, let me read the question. Okay, so the question was, can we apply the concept of F sequential and F par? So that is the fraction which is sequential and fraction which can be parallelized in a bit different way. So the student is suggesting some methods, and now we can keep it open to discussions and open to thought about what we can do with the proposed idea. So the proposal or the question type proposal given by the student is that if we consider load stores operations as the parallel component, because they can be scheduled to fetch and run parallelly, and the ALU operations as sequential because they need to be executed atomically. So can we do this division as such? And is there anything fundamentally wrong in looking at the execution in this particular manner, that is the proposed manner? And then, so this is an open question to have a problem formulated to speed up uniprocessors. Okay, so in the uniprocessor setup, the proposal is that can I have the ALU operations as sequential component and the load stores as parallel components? Okay, so when we studied this topic, we said what are parallel components? Those which can be executed parallelly. So if I can do a computation including the memory access in parallel, that would actually give me a speed up. If I am only doing load stores in parallel and I leave the ALU operations sequential, it of course it's a good idea, it will help me speed up, but I would try to draw an analogy or give you a design which is similar to what you're proposing, is the prefetch operation. So most of these caches have a memory prefetcher which before time goes and reads memory locations and loads them into the cache. So the prefetching of memory happens. So what you're saying, FPAR, so that has already happened in the background. And if we say that I do not do prefetch and I want to do FPAR as the loads and stores, but the memory access latency or even the cache access latencies are so high that in spite of doing them in parallel, our ALU will have to wait for the operations to, or the operands to be ready to start computing. Okay, so ALU operations are sequential and memory operations in parallel would mean that you better bring them in advance before the ALU wants them. So that's the only optimization which I can think of right now, which will improve the uniprocessor performance. And the prefetching is very readily being implemented or is already existing in most of the commercial processors. Okay, so when you are seeking for such optimizations, what you should make sure is that the processors which are running at very high frequency, we should give them more work to do. That is, the compute should be made parallel, which will give you more effective performance, and the memory accesses can be done more in background, like the prefetcher, or if you have to fetch a big array or blocks of arrays, then you can even parallelize that by interleaving the accesses, by distributing the memory elements across different memory banks or modules. So your memory can be divided into small banks, or it can be a distributed memory where your data is sitting at different physical locations. So there you can parallelize that by parallelly accessing all these memory modules to bring the data in one go to your processor. So at the memory level, parallelism can be established this way, but I'm not very sure whether I can, in your proposal of a sequential uniprocessor system, can I just say that the loads and stores are parallel component FPAR and F sequential is the ALU. Okay, but I appreciate your idea. It's a good thought. So you can take this thought further and concentrate on making the memory accesses faster and parallel to improve your uniprocessor performance. Okay, thank you for your query. Okay, so we'll take the next question. One minute. Right. So another question is about what are the different ways in which we can modify the microarchitecture level system in the Gem 5 simulator. Is it done in C++ or System C? And which of that is good for a beginner? Or is there any other way to change microarchitectural level features in Gem 5? Okay. So for Gem 5, there are good tutorials available online. But to be very frank, my research group has not worked at the level of changing the microarchitecture in Gem 5. So I do not have answers right away, but you can contact us separately and we can give you some pointers. But as far as my knowledge goes, everything is in C++ because Gem 5 is a modular or object-oriented system, and even the processor, the caches, everything is a C++ class. So most of the implementation is at the level of C++. So you can contact us separately. We can give you pointers to some Gem 5 tutorials. But right now, I do not have an answer because we have never worked in changing microarchitecture in Gem 5. Thank you very much. Okay, we'll take up the next question. So this question is from the live session. So somebody's asking that can we execute a PHP script on a multiprocessor machine, and how can we use both the processors to execute the script? Okay, right. So like any other program, PHP script is also an application. It has a sequential set of instructions. And when you have a sequential program, it can only run on a single core. But if you want to parallelize the application, you have to use the concept of either multi-programming or multi-threading. So you can have multiple copies of this PHP script doing variety of tasks, or you can have one single program which you can divide as a multi-threaded program. Okay, so you can make a multi-threaded version or run the PHP scripts as independent instances on different processors so that they can handle different types of requests on your web services. So that's what I can think of right now. Maybe if you have any comments, you can post and then we can take the discussion further. But multi-threading is the only solution which I can think of right now. Okay. And let me see if there is any more question. Okay, let me check. There's some new question coming. Yeah. Let me take the next question, which was submitted prior to the session. So the question is, the student says that they couldn't understand the meaning of pipelining, and Can I please explain it in general and also in the context of vector processors? Okay. So the concept of pipelining. Right. So actually the problem is in an interactive class, I can find out what exactly your doubt is. But here, because the question is very general, I think I will start with a very basic answer and then, or rather I'll give you a more detailed answer. So you can pick the portion which is relevant to your query. Okay. Right. So what is the meaning of pipelining? So most of you already know that the concept of pipelining through examples like if you have a car manufacturing factory, right? So if you have say 10 employees, not all 10 of them manufacture the car from scratch. What do? There is one set of employees who look after the frame of the car. There is another one who concentrate on the engine. Some look at the tires, the axle and other things. Some will look at how to paint the car, how to manage the interiors and so on. So there are variety of small teams which take care of individual aspects of the design and manufacturing of a car. And you have to then schedule these or order them in such a way that what should be done or which action should be done to begin with. Okay, so suppose you need to lay out the frame in the beginning, so you will have the frame ready. So once your one frame of the car is ready, the frame is handed over to the next team to fit the doors, for example, or do the painting. But the team which designed the frame, that is who did the welding and the molding of the frame, will go on to do the same thing for the second car. So they are experts only in the frame making. Then there is another team who is expert in the painting of the car. So once they paint one car, that car moves forward, then they take the next car and paint that car. So each team is responsible for only one task. So what happens in this? If I have 10 such steps or 10 such actions through which a car gets manufactured, I don't need one person to be expert of all the 10 tasks. Okay, I need a person or a team to be expert of only one task, and I need 10 such teams. So when I have 10 such teams, each team is doing only their task and then forwarding their output to the next team. So this is pipelining. Do task one, finish that task, give that to the next team to do the task two, and the first team continues to do the task one. Advantage of this is that the local expertise of the team is very nicely utilized. That is, one team need not be expert of all the components or all the design aspects of a car. Okay, they only concentrate and improve on their task. And then when the car moves through this pipeline, eventually you will get a finished product outside. So how long will this product take to come out? It will depend on the number of stages, that is number of teams who are working on this. For example, I said we had 10 teams. So if each team is going to take 1 day to do the work, at the end of 10 days, I'm going to get one car as an output. Okay, the first car comes as an output at the end of 10 days. When is my second car going to come as an output? Will it come at the 20th day or the 11th day? Okay, so you can pause the video, think for yourself, but I think you have by now guessed the answer, that when the first team finished its task and moved the product, the team 2, it started doing the task 1 on the second car. So while the first car was moving through this pipeline, the second car was already following it in the previous stage of this pipeline. So end of 10th day, I get my first car out, and end of 11th day, I get my second car out, because by the time the second car had already finished, most of its functionality is being processed. Okay, so that's the concept of pipelining, where every module or every team can be optimized to do the best of what work they want to do. And although the latency of the car manufacturing will be more here, because it adds to certain delays, communication delays between team 1 to team 2 to team 3, and maybe some extra resources, because if 2 teams are doing painting, one is painting the frame and the other is painting the doors, and then somebody else will fix them together, then we would need 2 copies of the paint brush and the paint boxes, right? So you will have to duplicate the resources at times, and you will need some extra storage and extra delay for communicating between the teams. But apart from these little overheads, overall, what have you got? You have got a very good throughput. That is, you're getting 1 car manufactured every day after the 10th day. So your initial latency, the latency of car manufacturing per car is 10, but your throughput is 1 car per day after that. Okay, so that's the basic concept of pipelining, where we do the work in this particular manner. Bringing that same concept to a processor design, what happens in a processor? You have to first fetch an instruction, decode that instruction, execute it, and then the results have to be written back to the memory. Okay, so these are 4 to 5 stages in which a processor works. So when I divide this sequence into small stages, which are called pipelining stages. So the first stage will do the fetch. So they will just bring the instruction from the memory. Once they bring the instruction bit stream is given to the next stage. So the current stage 1 will not do anything except bring the instruction from memory and give the instruction to the stage 2. Once it hands over the bit pattern of the instruction to stage 2, the stage 1 again goes and fetches the next instruction. So it is going to only do the task of go to memory, bring instruction, go to memory, bring instruction. And what does the second stage do? Second stage has to do the decoding. Because the first stage has given it an instruction, the second stage duty is to decode this instruction, that is, understand what to do with this instruction. Is it arithmetic instruction, a logic instruction, or a memory instruction? So it looks inside the bit pattern and finds out what to do. Once it understands what to do, it prepares the ALU, or it prepares the operands to be given to the arithmetic unit after doing the decoding. But this stage 2 is not going to do the addition multiplication for us. It is only going to say that, hey, multiplier, you have to do this. Hey, adder, you have to do this. And it simply hands over the task to the next team, which is the ALU. And now the stage number 3, which is the ALU, will do the actual arithmetic operation. Okay. And while the arithmetic operation is happening in the stage 3, the stage 2 again starts decoding the next instruction. While the second instruction is happening, the first stage is bringing the third instruction. Okay, you're seeing this. So the pipeline gets filled with sequential 1 by 1, lots of instructions get pushed in, and we get a good throughput in a pipeline processor. Okay, now this is in a single threaded or a scalar processor. So when I go to a vector processor acts on a vector of instruction. That is, it is going to operate on multiple data items. So you can, so such processors want to speed up. So if every operation is say a division or a multiplication or even addition, which is 64-bit addition, right? So we will need adders which are very big in size. Right, so it is, so there are many arithmetic unit designs in the market or in the research community, which also go for pipelined design. So the adder itself is pipeline, the multiplier itself is pipeline. Okay, so that's the concept of having pipelining within the functional units. So you can have an adder which is pipeline, and this adder, what does the vector processor do? It has to do, say, 10 additions on a vector of size 10. So either it has 10 adders which does them, or if it has a single adder, it can have a pipelined adder and schedule these different 10 additions one after the other to the adder, and then the output is collated at the bottom. Okay, so these are very design specific decisions, but both ways are possible, that you have several copies of the adders, or if you have lesser copies of the adder, it is desirable that they are pipelined so that we can schedule multiple additions in one go on the pipeline adders. In the lectures, we also saw that the vector processors also can be replicated as lanes, right? So I have one pipeline adder, and I can have 4 such pipeline adders which are executing 4 parallel vector instructions in the same go. Okay, so there are many options in which we can exploit the concept of pipelining as well as parallelism to get good throughput. Okay, thank you. Right, so we'll go on to the next question, which has been posted in the form. Let me read out the question. So this question is related to cache coherence. So the situation or the scenario goes as follows. Okay, so say the stored value by a processor P1 is in the commit stage, waiting for the ROB commit instruction. Okay, but at the same time, P2 processor has already committed and written back to the cache. Also, invalidate cache P1. How will this impact the data coherence between the processor, where value in P1 available earlier than P2? P1 is stalled due to some previous instructions. Okay, so let me understand, and then maybe we'll take this question. So for the learners who are not aware of what is an ROB commit instruction, I'll give some background. So processors either are sequential, which is they do just the old style processors, which only did one instruction at a time, but or rather they are called in order processors. But the current generation processors are all out of order processors. So what do? They look ahead in the instruction queue, and whichever instructions are possible to be executed, they will complete the execution. So it's like exploiting the instruction level parallelism. And if you have instruction I1, I2 to I5 to be executed, but your instruction I2 and I4 are ready to be executed because the data is available and I want to execute them. Whereas I1 is still waiting for some data. So I would say as a processor, let me do I2 and I4, but I will not write their answer. I will just finish the addition and keep the answer. And whenever my turn in the instruction execution comes, I will write the answer. So these instructions are then queued up in a buffer, which is called a reorder buffer, because this buffer is going to reorder the instructions in the correct manner of the program order, because program order is very important. It has to be maintained. So your instructions are in the ROB, and as and when their turn comes in the program order, they are committed. So committed means they will be the result of the instruction is written into the memory. Either it is cache or main memory. So commit means the instruction has completed its work. Okay. So the question is, suppose there is a store instruction in the reorder buffer which wants to write its data to the main memory. Okay. Now P1 is the processor who has this instruction in the ROB. So it's waiting for its commit instruction to happen. So it hasn't yet happened. It's waiting for its turn. But at the same time, P2 processor has already committed and written back the value to the cache. So P2 was also modifying the same variable. P1 and P2 was both wanting to write. P2 has already written in its cache, and P1 is waiting to write into its cache, but it is still waiting in its reorder buffer. So now, is there a coherence problem in this? And would P1 will have to stall, or what happens? I mean, is there a coherence issue in this particular scenario? So that's the question. Okay. Right. So Till week 4, I think we have seen only 2 small coherence protocols. As you study more protocols and you see more requirements or conditions through which correctness can be established, you would understand this concept in a much better way. I'll try to explain it at this moment, but if it is not clear, I would encourage that you wait for a few more weeks and see if you can understand the topic. Okay. Right. So when P1 and P2 both intend to write to a shared variable, the same variable is being has to be written by both P1 and P2. It is actually not possible that both of them would have the store instruction in their ROB, because the cache coherence and consistency mechanism makes sure that exactly one processor will have access to the data item which is to be modified. So I'm going to modify the data item. So if P1 is going to change the data item, the system takes care that P2 cannot have the variable with a writing permission. Okay, so there are 2 types of protocols, write invalidate and write update. So the easier one is invalidate. So when if P1 is intending to write to a variable, shared variable, then the coherence protocol makes sure that P2's variable is invalidated. So P2 will never have that variable available for doing its task. If P2 is doing the write, then P1's variable will be removed. So this is how such a condition will never arise in a cache coherent system. Okay, and one would say that what's the guarantee that if P1 says, P1 tells P2 that you remove the variable I wish to write, would P2 comply to it, or would P2 get the message from P1 before it can change? Okay, so the protocols are made foolproof that once P1 tells P2 that you remove the variable because I want to write, P1 has to wait until P2 has actually removed the variable before P1 can start modifying. So this guarantees that P2 will not have a copy, only P1 has the copy of the variable which it can change. Okay, and with this there is an assumption that the consecutive writes happen spaced out in time. I mean, they're not very close to each other in time duration. It is at the same instant in real life, P1 and P2 deciding to write and both of them completing it is not assumed when we are dealing with coherence. So this concept or this assumption will be removed when we do cache consistency models, where we will deal with conditions when both of them want to write it parallelly and how can we permit them, or if we don't want to permit them, what should we do? So that is the cache consistency issue, which we will take towards the end of the course. Right now, in cache coherence, we assume that at a time, only one processor can change, and 2 writes to the same variable are spaced out in time. I mean, they don't collide with each other in real life. So there is enough time between the 2 write instructions so that one processor gets enough opportunity to invalidate the copy of the second processor before it can start writing. Thank you. If you have any more doubts, you can put them on the YouTube chat or in the form which was shared with you. We have finished 4 weeks of this, almost 4 weeks of the subject, and I'll just read out the topics which we have studied as a quick recap for all of you, so that you can also recollect how much comfortable you are with this particular topic. Okay, so if we began that course with motivation about why do we need parallel architectures. That is the variety of applications which exist or which demand parallel processing. And then we looked at the multiprocessor revolution, which was very much needed, because without that we won't have parallel processors, and then the questions of how to use them and how to manage them won't have arisen, right? So multiprocessor revolution, why and how did it happen? We looked at that. And then we looked at what comprises of a parallel architecture. How did the system develop from there were only pure message passing systems earlier, pure shared memory systems, but then slowly with the evolution of compilers, operating system, and the layers of software management, we were able to execute any type of programming model on the same hardware platform. Okay, then we looked at different performance and benchmarking matrix and formula and so on. The next module covered most of the cache basics, which was again a repetition of a second year or third year level course, undergrad course, where we answered the different memory hierarchy questions. We looked at the cache design of a direct map cache, set associative cache, fully associative cache, and then the block placement, replacement policies, and so on. Then we had a detailed look at the virtual memory system and the associated design aspects of it. That was in module 2. And in module 3, which is currently going on, we have started looking at cache coherence. So you have understood the concept of cache coherence. That is, if you have a shared variable being used by multiple processes or multiple threads, then when one of them decides to change, how do you manage or how do you make sure that the others do not change it so that each of them gets the correct answer? So cache coherence says that if one processor writes value to a variable, then everybody else sees that most recently written value to that variable. They never get the stale value. They always get the most recent value in time, which is written by any processor in the multiprocessor setup. So for this to happen, we need a protocol, because you imagine you are so many friends are sitting in a class and you want to say something. So there has to be a coordination between all of you to allow or permit one of you to speak, because if both of you speak, then there will be collision of the sound waves and there will be noise created and nobody will understand what you want to say. So essentially, what do? You take permission from the group that you want to speak and you start speaking. When you have finished, then you kind of relinquish your permission. That is, you say that now I have completed. So what message you are telling is heard by everybody in the room. Then the second person can continue further and put his points. So this is how you will coordinate amongst yourself when only one person can speak at a time. Similarly, when only one processor can write at a time, these processors need to talk to each other and take permission. That is, who is going to do the write. Okay. Now the processor design, which I discussed in the beginning of today's live session, was a pipeline processor, right? Fetch, decode, execute, write back. So processor is a 4 to 5 stage pipeline processor, which is taught in textbooks, but real processors can be even 200 stage pipeline. But let us take, if I have a 5-stage pipeline processor, does the processor have any stage which is doing this permission business? Okay, so what did I say? A processor has to take permission from others before it starts writing to a shared variable. But my 5-stage pipeline processor has no such provision that it can talk to others and find out whether it can write. So the So essentially, the processors are kind of isolated from the system. They do not know that other processors exist, other processors have a shared data, which I am supposed to take permission before I start writing. Okay, so that's the scenario. So the cache coherent mechanism has to be transparent to the processor. So see how beautiful these all coherence protocols will be. The processor need not bother about what is happening. The processor simply writes to the variables. It doesn't bother to take permission. But who does this? Our cache coherence protocols will do this for us, or do this for the processors. Okay, so the protocols which we will study will be implemented in the cache controllers, and these controllers will then take the responsibility of contacting all the other processors in the system to tell them that now I'm going to write, you do not write to this variable. Okay, again, are the caches standalone being able to do this? Because the cache again is an integrated part of the processor. So you also need support from the external system. So you need a network interface, which will now understand what the cache controller wants. It will take these particular messages from the cache controller, go over the interconnect, and then tell other processors. Now, when I say other processors, am I directly talking to the processor? No, I'm not talking to the processor, but I'm talking to the network interface of that particular processor. So that network interface will take my message, give it to its cache controller, and the cache controllers, between these two cache controllers, the coordination will take place. Okay, so this way the processor is completely aloof. He doesn't know about all these coherent mechanisms. So the programmer, if you are a programmer, you would never come to know what is happening in a parallel multi-threaded system, but the hardware takes care that all your variables changes are happening consistently and coherently. Okay, so we are going to see 3-4 coherence protocols. One is a VI protocol, then MSI, MESI, and Dragon protocols. So in the next few weeks, we'll study 4 protocols in detail. So every time the protocol is slowly built in the lectures. So follow the philosophy behind them, because all 4 protocols are very distinct. They have their own good points, their drawbacks. And then we'll discuss the types of misses. So we have already seen cache miss. You already know that the data is not there. So you have a capacity miss, a conflict miss, and capacity, conflict, and what's the other third miss? Think and tell me. Yes. So the first type of miss, before you get a capacity or a conflict miss, you're going to get a compulsory miss, which is even if the cache is empty, there is space, you have never brought the data from the main memory. Okay. So the first time you bring data, that is the compulsory miss. So once you've brought lots of data, your cache becomes full, and subsequently you will get either capacity misses or conflict misses. So these are the 3 misses which we have studied till now. Next few weeks down, we will see a 4th type of miss, which is called a coherence miss. And again, it's a very interesting topic. So you can also revisit the videos if the concept is not clear. I've also done a detailed example to make you understand what are the different types of coherence misses. Even in that, there are small categories, and they are very interesting, because if you follow the idea of what a coherence is, that is, a variable is being shared by multiple processors, and now one processor does not get it. So when the processor does not find the variable, it's a cache miss. But what type? The question arises, did this processor never bring the block? That's why it is a miss. Or it had brought the block, but somebody else took it away, and that is why I'm incurring a miss. So such questions, if you have answers to that, you can very correctly identify the type of a coherence miss. Okay, so although the names may be very cryptic, or you'll think, oh, there are so many terms to define the miss, but they are all self-explanatory. So if you follow the storyline of that, the lifeline of the cache block going from one processor to the other, you will be very easy to identify the coherence miss categories. All right, students. So if there are no more questions, I've also given you some future topics, what we are going to cover. And it was a very interesting session that there were 6 to 7 queries, and they also covered different aspects of computer architecture as such, not only the cache coherence problems. So it is very nice that you are thinking, you are attending the lectures, and you are thinking beyond the course content about how to do certain things which are in your mind. So very good. Keep the inquisitiveness alive. And it is very important that we have people interested in architecture, in systems, because these are the building blocks for future machines. And you cannot just have applications. They are never going to run in the air. Even if they run on the cloud, they finally run on hardware, which is sitting somewhere around the world. So hardware systems have to be there. They have to perform efficiently. And as you do this course, you will understand that the processor design is so complex. So many things are happening in the background, which are readily given to the programmer, right? So to appreciate all that, it's good to do such courses. And I hope you will keep enjoying, and you will complete the course, take the exams, and do well in the subject. So thank you very much for attending the live sessions, taking the subject, do your assignments on time, and see you in the next month for the next live session. Thank you so much. Bye-bye.
Thank you, ma'am.
ओके, थैंक यू। आपका नाम NPTEL है, तो आपका नाम अच्छा, ओके, नाइस। थैंक यू फॉर योर हेल्प। नेक्स्ट मंथ मिलते हैं। बाय बाय। Thank you, TAs, and thank you, Nikhil and Shreyans, for joining online, and all the YouTube people. Thank you so much. Bye-bye.